Alright guys, welcome back to Underground Science, and in this video we'll be talking about, we'll be diving deeper into quantum numbers and figuring out some more stuff, alright? And make sure to watch my last video. I did a quick overview. I wouldn't say quick, right? I don't know, I think it was like past 15 minutes or something, but I did an overview of quantum numbers, of the four different quantum numbers, right? And then in this video we'll just dive deeper, all right? So let's quickly list out the four quantum numbers again, like we did in the last video, right? So we have our azimuthal quantum number, right? And that's our L. We denote that as L, or angular momentum quantum number, right? So let me write that down, L, all right? And then we have our, I don't know why I listed it right here like in this order, but second we have our principal quantum number, principal quantum number, all right? And just like we denoted our angular momentum quantum number as L, we have a symbol for our principal quantum number, which is going to be N, right? This is just energy levels pretty much. And then third quantum number, guys, is the magnetic quantum number, right? And again, if you want an overview of these, make sure to check out my last video on the overview of quantum numbers, all right? So magnetic quantum number, and then we denote this as M sub L, okay? And last but not least, our last quantum number that we talked about was our spin quantum number for our electrons, okay? So spin, oops, I don't know what happened there. Let's go and undo that. Spin quantum number, all right? So spin quantum number, and the way we denote that is M sub S, all right? So these are four quantum numbers, and we'll dive deeper into it in this video. All right, so let's go ahead and get started. All right, so let's start talking about the relationship between the principal quantum number and the azimuthal quantum number, or otherwise known as the angular momentum quantum number. All right, so pretty much, actually this is just a cool picture, right? Got for quantum mechanics. I just thought it was cool, so I just put it on here. All right, but anyway, let's scroll up. Let's use our space that we have. And so remember in the last video I said the principal quantum number was pretty much like if we draw the Bohr model here, right? We have an X amount of protons and X amount of neutrons in our nucleus, and then we have our first energy level, second energy level, third energy level, and so on, right? And then we have a set amount of electrons in each energy level. So the first energy level can only hold 2 electrons, and the second energy level can hold 8 electrons. All right, 3, 4, 5, 6, 7, 8. That's not good, but all right, whatever. So 2, 8, and then the third electron can hold 18. I'm not going to draw all 18, right? But we get the idea. So the relationship, though, between the principal quantum number and the azimuthal quantum number is this. When n is equal to 1, or otherwise our principal quantum number, when our principal quantum number is equal to 1, our azimuthal quantum number, our angular momentum quantum number, is going to be equal to 0. All right, so what's our relationship here? We just saw that, right? Actually, no, let's write more so we can see it in a more clear fashion. So when n is equal to 2, when our principal quantum number is equal to 2, we see that our angular momentum quantum number, our azimuthal quantum number, is equal to 1. And again, we'll write one more and we'll probably get it, right? When n is equal to 3, when our principal quantum number is equal to 3, our azimuthal quantum number is going to be equal to 2. So what's the relationship here, right? We see that our L, or our azimuthal quantum number, is equal to n minus 1, right? Because if we see this relationship here, our L is equal to 1 minus 1, which is 1 is our principal quantum number, minus 1 is equal to 0, and that's what it is. right? L is equal to 0, and you can see that same thing for when principal quantum number is 2, and for the same thing when the principal quantum number is 3. The azimuthal quantum number is always going to be the principal quantum number minus 1. All right, so that's the relationship between the azimuthal quantum number and the principal quantum number. And let's see the relationship between, all right, before we actually do that, so we can see that we get our azimuthal quantum number, right, our L values, based on the principal quantum number. So our principal quantum number decides what the angular momentum quantum number is going to be. All right, and we just saw that it's n minus 1. Our angular momentum quantum number is equal to our principal quantum number minus 1. All right, and now let's see the relationship between our, okay, sorry about that. Let's see the relationship between our azimuthal quantum number and our magnetic quantum number. All right, remember our magnetic quantum number just told us the orientations, all right, of the specific subshells, or of the orbital, and there's many subshells, right? So, and if you need clarification on that, you can just quickly go ahead and watch my overview of quantum numbers video where I talk about that, all right? But we'll get more into that, so don't worry. Okay, so let's write down the relationships, all right, just like we did for our principal quantum number and our angular momentum quantum number. Okay, so let's say if L is equal to 1, right, or anything, let's just say this right off the bat. If L is equal to 0, right, we see that our M sub L, or our magnetic quantum number, when our azimuthal quantum number is 0, is also 0. All right, because if L is 0, remember in the last video we said if L is 0, we have an s orbital. Well, an s orbital is just a sphere, and remember, magnetic quantum number tells us the orientations on a 3D graph. Well, a sphere only has one orientation, right? So that's why we have only one value, right? These magnetic quantum numbers, you have to look at it as specific values. So 0 is just one separate value, which means we have one orientation. All right, one orientation for our s orbital. One orientation for s orbital. All right, and we're getting a little ahead of ourselves right now. We'll talk about orbitals and orientations later, but right now let's just focus on the relationships. All right, so we saw that, right, when the azimuthal quantum number is 0, our magnetic quantum number is also 0, which means we have only one orientation, because we're looking at specific values. I know it's 0, but that 0 counts as a value, and that's only one value here we see, so it's one orientation. And L equals 0 means we are working with an s orbital. Okay, so s orbital and one orientation because of the magnetic quantum number. Now let's look at an azimuthal quantum number of 1. Okay, so if we have an azimuthal quantum number of 1, we see that we have a magnetic quantum number. Okay, I literally can't speak in any of my videos sometimes. We see that we have a magnetic quantum number of -1, 0, and +1. So right here, remember in the last video we drew a px, py, and a pz orientations for our p orbital, right? We have 3 different p subshells in our p orbital. We said it had 3 orientations. Well, this is why. Remember, when the azimuthal quantum number is 1, we're working with our p orbital, right? And our p orbital has 3 orientations. Now we know why, because the magnetic quantum number has 3 distinct values, and each value counts as an orientation. So we can see that the p orbital has 3 orientations based on the magnetic quantum number. Okay, so that's why we have a px, a py, and a pz. Okay, and another important thing to realize is that when L is equal to 1, we have these 3 magnetic quantum numbers, but we also have to include the previous azimuthal quantum number, which means when L is equal to 1, we also have to include L equals 0. All right, so overall, we're going to say this as this, or we're going to state it as this: L equals 0 and 1. All right, so what does that mean? Let's just chill out for a little bit and see what this means, okay? So L equals 0, we just said was an s orbital, right? So what does that mean? We have an s orbital here for 0, for our azimuthal quantum number of 0. And then we also have an angular momentum quantum number of 1. And what does that mean? We saw that that means we have 3 distinct values for our magnetic quantum number. And when our L equals 1, we said we were working with a p orbital. And because of our 3 distinct magnetic quantum number values, we have 3 different orientations for our p-subshells, right? So we have an S and we have a px, py, and a pz orientation. So that's what we're working with when we're talking about azimuthal quantum number is 1. We're talking about 3 p-subshells and the S-subshell. You can't forget about when L equals 0. So it's whenever you always have it in the back of your mind that for azimuthal quantum number, you can't forget about your other friends. All right, so your other friends being the previous quantum numbers. And we'll see that more. All right, so let's keep on making sense of this. So when angular momentum quantum number is 2, right, when it's 2, our magnetic quantum number we see is going to be -2, -1, 0, +1, and +2. All right, these are just representing values. It doesn't really mean anything except for that. It just means that this is one value, this is another value, another value, another value, another value. We see 5 values here. So we know we're working with some orbital that has 5 different orientations. All right, and so L equals 2, we said in the last video, we're working with a d orbital. All right, and a d orbital has 5 different orientations. And why is it 5? Because we have 5 values for our magnetic quantum number. Okay, and before we move on, maybe you noticed the pattern already, right? The magnetic quantum number is equal to our negative of our azimuthal quantum number all the way inclusive, right, to our positive azimuthal quantum number. All right, and we notice that because see, we have 2 right here as our azimuthal quantum number, and if we follow this rule right here, our magnetic quantum number is going to be, well, L is 2, so it's going to be -2, and we said inclusive, so -1, 0, all the way to 1, and then +2, right? We end at our azimuthal quantum number, but on the positive side. So that's how you figure out the magnetic quantum number based on the azimuthal quantum number. So you can see that everything ties up to our principal quantum number, right? Without a principal quantum number, we can't decide our azimuthal quantum number, and without our azimuthal quantum number, we can't decide our magnetic quantum number. All right, so all ties together. So let's go and write that down real quick. Okay, so let's get back to this. So when L equals 2, when our angular momentum quantum number equals 2, we know we're working with a d orbital. But how many orientations did our d orbital have? How many subshells, we should say? Well, our d orbital will have 5 different orientations, all right? Our d subshell as a whole will be oriented 5 different ways, just like our p subshell is oriented 3 different ways. And our S subshell is just a sphere, so it's only oriented one way, right? But remember, we just said in the previous, when we're talking about our p orbital, right? We do have L equals 2, but at the end you have to remember that we have our previous friends, right? You got to call them along too in the party. So it's L equals 0, L equals 1, and L equals 2. So I know we were just talking about angular momentum equals 2, but you can start off by that, right? You can like break down the problem by that. So when L equals 2, first thing you should know, okay, d orbital. But then you're just like, okay, how many orientations will my d subshell as a whole have? How do I find that? Oh, okay, we have to find the magnetic quantum number. Well, how do we find the magnetic quantum number? We say negative L to positive L. Well, good thing is we already know our L, so just literally write it out, right? -2, -1, 0, 1, 2. And then you're just like, okay, now how do I find the number of orientations I have? We'll just count the number of values that you stated in your magnetic quantum number range, which is 5. So we know a d orbital has 5 orientations. Okay, so 5 orientations. And then after that, once you find the magnetic quantum number, you're pretty much done, like you could say, breaking down the problem. And then make sure to write down the previous quantum numbers too, and below it write down, all right, L equals 0, we said was an s orbital, right, and only has one orientation, L equals 1. Remember we said was the 3 P-subshells, so Px, Py, and Pz. And then we just said that we had a D-subshell or D orbital for L equals 2, and we said that D has 5 orientations. All right, so just say 5 orientations. And this will really come in handy when we talk about how we get the 2, 8, 18, 32 pattern for our Bohr model, why there's only 2 electrons in the first, energy level 8 in the second, and so on. So let's just keep that in mind, okay? And last but not least, let's talk about our F orbital, or our F subshell. And that's going to be when we have an angular momentum quantum number of 3. Okay, when we have an angular momentum quantum number of 3, we're talking about a F orbital, all right, an F subshell. And then if our angular momentum quantum number, if our angular momentum quantum number is 3, we know that our magnetic quantum number is going to be negative L to positive L, right here that we said. So we're going to have negative 3, negative 2, negative 1, 0, positive 1, positive 2, and positive 3. All of these are magnetic quantum numbers. And because we have 7 distinct values, okay, we have 1, 2, 3, 4, 5, 6, 7. This means that our F orbital will have 7 different orientations, all right, 7 subshells. Okay, so 7 F orientations. All right, let's just write that. And these are 7 different subshells. Each subshell is going to hold 2 electrons. Okay, let's keep that in mind for our next video when we talk about the 2, 8, 18, 32 pattern, right? So let's just write that down and let's get that in our minds. Each subshell, right? And what I mean by each subshell is that if you take the P subshell, for example, P orbital, we saw that it has 1 subshell, 2 subshells, 3 subshells, right? 3 different orientations. So that's what I mean by each subshell. So each subshell will hold 2 electrons. All right. So let's just keep that in mind. So now, I mean, we just covered it all, right? But it was probably pretty confusing, but hopefully it wasn't, right? Just remember that when we're talking about deciding the quantum numbers, we just have to we just have to think about first, like step by step. All right, so the first step you're going to do is, actually, you know what, let's just do a short review on the next page. So the first step you're going to do, right, if you get like a principal quantum number, remember, everything depends on the principal quantum number. So if you have like an energy level of like 3, right, if you're talking about an energy level of 3, which is also the principal quantum number 3, all you have to do is like, okay, so what do I do next? Well, we know angular momentum quantum number, or the Azimuthal quantum number, is just n minus 1, right? So that's easy, right? So let's do it in a different color. Straight up, we just write, all right, angular momentum quantum number is n minus 1, so it's going to be 2. All right, so now we know that once we decide it's 2, remember we said that the Azimuthal quantum number decides what orbital we're talking about. So if L equals 2, what were we talking about? We're talking about the D orbital, right? So we can write that down real quick on the side, right? D orbital. The more we just write it down, the more clear it's going to be for us later on, right? So L equals 2 is the D orbital. Now what do we do? All right, well, how many different subshell orientations does the D orbital have? Well, to figure that out, we use our awesome magnetic quantum number, all right? And remember, our magnetic quantum number is equal to inclusive from our negative L value all the way to our positive L value. Well, guys, we already found our L value, right? I mean, we already have it right here. So all we have to do is just write it out one by one. So -2, then -1, then 0, then +1, and +2. All right, and what do these numbers mean? These are distinct values. Each value represents an orientation. So based on these distinct values, we have 1, 2, 3, 4, nope, that's not a good circle, 4, and then 5. That means we have 5 different, I don't know why I put a dash there, but 5 different D orientations, all right? D subshell orientations. and each subshell orientation will hold 2 electrons. Remember we stated that in the previous slide? So 5 different D-subshell orientations. All right, so now we know that. We just have to say that, okay, now that we talked about L equals 2, we can't forget about our previous friends. And the reason why I keep on saying that is because it's going to come in handy later, all right? And probably in our next video. So then at the last, we just have to write L equals 0, L equals 1, and 2, okay? So it's everything previously, too, also, for Azimuthal quantum number, all right? And the reason we write this is because later we'll see that we'll need to write this to know what we're working with, because then we'll know, like, okay, so when L is equal to 2, we're working with an S orbital, we're working with our 3 P subshells, right? Px, Py, Pz. And on top of that, we're working with our 5D subshell orientations, right? So 5D orientations. That's why you have to know, you have to make sure to remember the previous Azimuthal quantum numbers too, quantum numbers also, okay? So that's pretty much it. That's the basic ideas. We're just trying to get in the hand of recognizing the principal quantum number, and then calculating the Azimuthal quantum number based on the principal quantum number, and then we're trying to calculate the different orientations, right? The magnetic quantum number based on the Azimuthal quantum number, and then we're just stating the previous friends. All right, just think of it like that. Okay, so that's pretty much it. We got in the hand of these different steps, which is going to help us in figuring out exactly why we say that we have 2 electrons can only fit in the first energy level, then 8 electrons can only fit in the second energy level, and then 18 can only fit in the third energy level, and then 32 and so on. Remember that? Remember that pattern we used to talk about when we talked about the Bohr model? Well, why is that, right? We just have it down like 2, 8, 18, 32, but we can look at the periodic table and figure out why, or we can even go deeper and calculate the magnetic quantum numbers for each principal quantum number, and then figure out why. All right, so that was probably a lot, and hopefully you guys, hopefully it made a little sense to you guys. All right, I just hope that it can make more sense to you guys in my future videos, and everything can tie together for you guys. All right, so hopefully I see you guys in my next video, where I'll probably be talking about this again, the pattern, and we'll be working with quantum numbers even more. And don't forget to hit that notification bell. And also, guys, don't forget to subscribe and like. All right, and see you guys next time.